Hey there, and welcome. You know, when you really boil it down, the entire field of machine learning is basically a quest. It's this massive search for answers that are hidden inside mountains of data. And like any great quest, it all starts with a couple of really fundamental questions that, honestly, drive everything we're about to dig into. So, first up, you've got this world of options, all these different tools and algorithms. How in the world do you pick the perfect one for the job you're trying to do? This is a challenge that every single person in this field faces, whether you're a seasoned pro or just starting out.
And then, right on the heels of that, once you've picked your tool, how do you make it better? How do you sharpen it, tune it, and get it to perform at its absolute best? These two questions, really, they're the two pillars holding up this entire fascinating world.
Now, just to make sure we're all starting from the same place, let's lock in a clear definition. At its absolute core, machine learning is all about building systems that can automatically find meaningful patterns in data, and then, and this is the magic part, using those patterns to make really smart predictions about the future. It's literally about turning raw information into foresight.
Okay, so let's dive into that first big question. Because before you can even think about choosing the right algorithm, you have to be totally crystal clear on one thing. What is the actual problem you're trying to solve here?
I think the best way to wrap your head around this is with a simple analogy. Think of all the machine learning algorithms out there as tools in a master craftsman's toolbox. Each one is built for a very specific job. Your role, as the craftsman, is to deeply understand the task at hand so you can pick the right tool. Simple as that. You wouldn't use a hammer to saw a board, right? It's all about matching the method to the mission.
And that mission, well, usually sends you down one of two main paths. It's like a fork in the road, and the path you take depends entirely on what your data looks like. Do you have data with helpful labels? Are you flying blind with data that has none?
This right here is a perfect picture of that first path. It's called supervised learning. What's happening is the machine is being fed a bunch of examples that are already sorted correctly. These shapes are already in their yes and no boxes. The machine's job is to study these labeled examples and figure out the rules. It learns what makes a shape a yes, so that later it can try to classify a brand new shape it's never seen before. And that brings us to what is without a doubt the single most important goal in all of machine learning: generalization. See, it's not good enough for a model to just memorize the answers it saw during its training. I mean, anyone can do that. The real test, the whole point of it all, is whether it can take what it learned and make correct predictions on new data it has never, ever encountered before. That's the magic trick.
So how does a machine actually see these shapes? Well, it doesn't see pictures like we do. It sees neat, organized data. This shows how each object gets broken down into its key attributes, or what we call features, things like its color, its shape, and so on. Then each set of features gets paired with a label, in this case, a 1 for yes or a 0 for no. This is the precise language the machine speaks.
Okay, so if supervised learning is kind of like studying with an answer key, what's the alternative? Well, that would be unsupervised learning. In this world, the machine gets no labels, no answer key, nothing. It's just given a giant pile of data and is basically told, go figure it out. Its job is to find the hidden structures and natural groupings all by itself, without any human nudging it in the right direction.
And believe me, this isn't just some abstract idea. It is happening everywhere. Unsupervised learning is what astronomers use to discover completely new kinds of stars in the cosmos. It's how e-commerce sites group you with other shoppers who have similar tastes to give you those eerily accurate recommendations. And it's how biologists can spot different clusters of cells in their data, which can lead to incredible medical breakthroughs. It's a seriously powerful tool for discovery.
All right, so we've picked our approach. We've chosen a tool from the toolbox, whether it's supervised or unsupervised. And that leads us smack into our second big question. Once you have the tool, how do you actually master it?
Which brings us right back to this critical challenge. Look, having the right algorithm is only half the battle. Now we've got to tune it, we've got to refine it, we've got to optimize it to squeeze out every last drop of performance. So what do we even mean by optimization? It all comes back to that one key metric we talked about: generalization. We're just tweaking all the internal settings and knobs on the models so that it gets better and better at making predictions on new, fresh data. This whole process is what turns an apprentice model into a true master craftsman.
And trust me, that toolbox is huge. We're not talking about just one type of hammer or one kind of saw. There is an entire universe of different models out there, and each one has its own unique way of thinking and learning. For instance, you've got models like this, called graphical models. They're specifically designed to draw a map, basically of the complicated web of relationships between a bunch of different factors. They let us actually see how everything is connected.
And then, on the complete other end of the spectrum, you have something like a neural network. These are fascinating because they're actually inspired by the biology of our own brains, with all these layers of interconnected nodes that process information in a totally different fashion. It just goes to show you the wild variety of tools at our disposal.
But here's the kicker, and this is so important. It doesn't matter if it's a graphical model, a neural network, or some other crazy thing from the toolbox. The basic idea of optimization is always the same. For any model, the goal is to fine-tune its internal settings, all those countless little knobs and dials, to make it as accurate and as reliable as it can possibly be when it faces new data.
So, what's the thread that ties all of this together? From picking a tool to mastering it, from learning with labels to learning without them. What's the one common language, the secret ingredient that's underneath all of machine learning? Well, the answer is probability.
You know, more than 200 years ago, this brilliant mathematician, Pierre Laplace, he just nailed it. He said probability theory is nothing but common sense reduced to calculation. And that idea, well, it's just incredibly profound.
Because that is exactly what machine learning does. The real world is uncertain, right? Data is almost always messy and incomplete. So machine learning uses the strict mathematical rules of probability to manage all that uncertainty, to weigh all the evidence, and to make the most sensible guess it possibly can. It takes that fuzzy idea of a best guess and turns it into a sharp, calculated insight.
So, I want to leave you with this final thought. If machine learning really is, like Laplace said, just our common sense turned into pure calculation, it makes you ask a pretty mind-bending question about our future. What happens when our calculations get so powerful that they start to find patterns and reach conclusions that go way beyond the limits of our own common sense? Definitely something to chew on. Thanks for joining me.